Okay, I guess the screen is visible and my voice is clear. If that is the case, I think we can start solving some problems. Okay, so let's start with the first problem. And the problem is, what energy is needed to ionize a H atom which is in its first excited state. And your options are minus 13.6 eV, plus 13.6 eV, minus 27.2 eV, or none of the above. Okay, so we have an hydrogen atom. Let's say this is the nucleus. Okay, and let's say this is the ground state, and then this is the first excited state, and so on. We have other more excited states. Okay, so the electron, where will the electron be? What do you mean by first excited state? Anyone?
So going from first shell to second shell.
Yes. So because it is said that hydrogen atom is already in its first excited state, it means that our electron is somewhere here, right? It is not in the first shell, but it is in second shell. If it was in the first shell, we will say that it is in ground state. But because it is in second shell, we will say that now it is in first excited state. Now, what do you mean by ionize? Ionize. So ionize means that you want to remove the electron. So remove this electron, and that will require some energy, right? We will require some energy to remove this electron. And now we have to answer the question that what is this energy which is needed to ionize an H atom? That is, what is the energy that is needed to remove this electron completely from this first excited state? Okay, so when you solve this, okay, so first of all, what is the energy of an electron? Let's say you have an electron in the ground state. Okay, energy of electron in ground state. How much is this value in electron volts?
Minus 13.6.
Yes, minus 13.6. And we know when we go to first excited state, that energy goes as n squared, right? So this will be minus 13.6 divided by n square. And what will be the value of n here? So this is n is equals to 1, this is n is equals to 2, correct? So this will be minus 13.6 divided by 4. Okay, I lost my connection briefly, but that is all right. So now this will be minus 13.6 divided by 4. Got it? So this comes out to be minus 3.4 eV. Okay, so the energy of this electron here in the first excited state, this is minus 13 point, sorry, minus 3.4 eV. So what is the energy that we need to give to the electron so that it is completely removed? It will be the same energy, right? So energy required to ionize for ionization, E is E ionize, that will be plus 3.4 eV. Right? So the answer will be none of the above. Any doubts in this one? Okay, I hope not. So let's continue to the second problem. So you have second problem. First line of Balmer series. You know Balmer series, right? Balmer series is, for first line it will be n is equals to 3 to n is equals to 2. Hmm? Is 656.5 nanometers. What is the wavelength lambda of first line of Paschen series? So for what is Paschen series? The first line will be n is equals to 4 to n is equals to 3. Okay? This is all given to us. And the options that are given to us are 1313, 328.25, 1875.7, and 164.125 nanometers. Okay. Now you know that for hydrogen atom, depending on the transitions, so if the electron is coming back to n is equals to 2 level, then it is called a Balmer series. Similarly, if it is coming to n is equals to 3 level, then it is called a Paschen series. And it is first line because it is coming from one level above. Okay. And similarly for here, it is coming from one level above. So let us draw all the levels. So I will say this is 1, 2, 3, 4, and so on. Okay. So how will the Balmer series look? So for the first line of Balmer, we have this transition, right? And for Paschen, we have this transition. And we are given that for Balmer, the wavelength is 656.5 nanometers. And we have to find out what will be the wavelength here. So this is clear, right? Now, how do you go about solving this? Now, once you know, do you? I guess everybody knows the Rydberg formula. So it tells wave number, which is nothing but 1 over lambda, that is given by r times 1 over n1 squared minus 1 over n2 squared.
Sir, option
Option
number
number
C.
C. Option number C. Yes, correct. Option C is definitely correct. So this problem is based on this Rydberg's formula, right? When you have when you have the Balmer series, so you can see that it is going from 3 to 2, right? So n1 is your n1 is 2 and n2 is 3. Okay, so let me call this Balmer series. Okay, so then your 1 over lambda b, this becomes r into 1 over 4 minus 1 over 9, and if you solve this, this will become r into 5 by 36, right? Similarly, what you will get for Paschen series, that will be 1 upon, let me call it by p, is equals to r into, now for Paschen series, your n1 is 3 and n2 is 4. So it will be 1 over 3 squared, which means 1 by 9, and 1 over 4 squared, which means 1 over 16. So this will become r times, I guess, 27 upon, no, not 27, just 7 upon 16 into 9. Correct? So if we, so let's say this is equation 1 and this is equation 2. If we divide equation 1 by equation 2, what will we get? We will get lambda p by lambda b is equals to, so r's will cancel out. Okay, let me write it. R into 5 over 36 divided by r into 7 over 16 into 9. So these r's will cancel out, and what you will be left with is 5 over 36 into 16 times 9 over 7. So if you cancel out, so this is 4, 9, and this 9. So this is 20 over 7. So your lambda p will be 20 over 7 lambda b. And lambda b is given to us as 656.5 nanometers. Okay, so your lambda p will come out to be 187.5, 187, 1875.7 nanometers. Okay, and this was option C. Okay, any doubts in this one? No. Okay. Okay, now I'll draw a few series, and I want you guys to tell me which series I'm doing. So let me first draw the levels. Okay, so these are n is equals to 1, 2, 3, 4, 5, 6. Okay, so if the transition is happening like this, what level is this?
Sir, Lyman series, ultraviolet radiation.
Yes, Gary. So this is your Lyman series. How about this one?
Sir, visible spectra Balmer series.
Yes, correct. And this one?
Sir, infrared spectra and Paschen series.
Yes. So these two, we just solved the previous problem, right? So in the previous problem, we were dealing with this transition and this transition. Okay, let's move on to the next one. What will be this series?
Infrared radiation and bracket.
Yes, correct. And lastly, this one?
So FUD.
Yes. So this is Lyman, and this was Balmer series. Okay, and then we have Lyman, Balmer. The your Z1 is your Passion series. This blue one is your Bracket series, and this yellow is your Fund series. Okay. So next question. Compute lambda for H beta spectral line. What is H beta spectral line? This is second line of which series?
Sir Balmer.
Yes. So what will be the transitions? So Ni is equals to and Nf is equals to.
So Ni will be 2 and Nf will be, sorry, Ni will be 4 and Nf will be 2.
Yes, correct. And the Rydberg constant is given to us 1.097 10 to the power 7 per meter. Okay, so let me give you options: 345, 486, 539, 602. So the Rydberg's formula gives us here Ni is, sorry, Nf is 2, so it will be 2 squared minus 1 over 4 squared, right?
So option number B.
Yes, correct. So then this will become R into 3 by 16. Yeah, okay. So your lambda will be 16 over 3 R. And if you put in the values, you will get 486 nanometers. Okay. Any doubt in this one? No? Okay. If not, let's move on to the next one. If K is kinetic energy and U is potential energy, of an electron, in H atom, then your options are K is minus U over 2, K is U over 2, K is minus U, or K is minus 2U. Okay,
So option number A.
option number A. Yeah, this is correct. Okay, so so for a hydrogen atom, we we kind of know, right? If your total energy is E, then that total energy is for that your total energy is K plus U. And when you solve this, so what you get is that your K is minus U over 2. Okay, but you can also do it fundamentally. So you can consider that you have a nucleus here and an electron at some distance r, right? So you can write out the mm, expressions for K and Q. So for example, because it is a hydrogen atom, this charge is E and this charge is also E, proton and electron. This is plus E and this is minus E. So your U becomes 1 over 4 pi epsilon naught, okay, E squared minus E squared over R, correct? This is the expression for U, okay? And if you now write for your kinetic energy, if the mass of this electron is m, okay, then you can write half m v squared. This is the value of your K, okay? Now what you can do is you can use the quantization condition. You can use quantization condition, which gives you mvr is n h cut, okay? And then if you do that, then what you will get ultimately is this, that your K is 1 over 8 pi epsilon naught E squared over R. And if you compare it with U, so this will simply become minus U over 2. Therefore, option A. Okay. So let's solve next problem. Black body radiates heat at the rate of 5 calories per centimeter square per second when its temperature is 27 degrees Celsius. Temperature of another black body is 627 degrees Celsius, what will be the rate of heat radiation? Okay, and your options are 116, 405, 5, and 45. Okay, okay. Does anyone know how do you go about solving such problems?
Sir, would we using the formula U is equals to sigma T raised to the power 4?
Yes. Can anyone tell me the name of this equation?
Sir, I don't remember it, sir.
Okay. Anyone else? It was there in the lecture.
Sir,
Any
it was
guesses?
not Wien's displacement.
No, it is not Wien's displacement.
No. So that's lambda mt is equals to constant, right?
Yes, yes, yes. Hmm. Anyone else? Any guesses? Okay, no problem. So this is Stefan's law, or also sometimes called Stefan Boltzmann's law. Okay. So this was there in the lecture, and what it says is, it basically says that your energy which is emitted, that is proportional to T to the power fourth. And here your temperature, T is your temperature. And one very important thing to note, that what is the units of this temperature. So should we use Celsius, Fahrenheit, Kelvin? What should we use here? So in this equation, we always use Kelvin, okay? Because Kelvin is the absolute temperature unit, right? It starts from zero and goes all the way in the positive direction. There is no negative temperature in Kelvin scale, right? If you use Celsius, you can see it is already T to the power fourth. So minus 30 degrees and plus 30 degrees will give you the same answer, right? But that is not what you will observe physically, correct? Okay. So first thing then what we need to do is convert these temperatures which are given to us to the Kelvin scale. Okay. So let us solve it. So for the first body, the temperature is 27 degrees Celsius. It will become 300 Kelvin, right? And it is emitting some energy which is 5 calories per centimeter square per second. Okay. Now we have another body which is 6 to 7 degrees Celsius, and its temperature will become how much? 900 Kelvin, right? And now we want to find out what is the energy that it will give us.
Sir, option number B.
Option number B, yes. So you can clearly see that 5, sorry. So let us call this x. So x over 5 will be 300 over, sorry, 900 over 300 to the power 4. Okay, and then this is just 3, and this is 81. So your x is 5 times 81, which is 405. Okay, which is option B. Correct. So your Stefan Boltzmann law, it tells you that if you increase the temperature by 3 times, as was the case here, we increase the temperature 3 times from 300 to 900. So the rate of heat radiation that increased by 81 times, which is 3 to the power 4, right? Because it is proportional to the fourth power. Okay, any doubts in this one? No? Okay. Okay. Let me give you one conceptual question. You don't need to solve this, but I want everyone to type their answers in the chat box or unmute your mic and tell me what answer do you think is the answer to this problem. Okay. So your question is, under identical conditions, a black body absorbs heat in compared to a white surface. And your options are equal, negligible, more, less. Okay, tell me your answers. Take 1 minute to think if you want. Type in the chat box, open your mic, however you feel comfortable doing it, and I'll wait. You don't need to solve anything in this, right? You just need to think about it. This is related to your black body problem. And why do we call it a black body? A. Okay, good. Other people?
So option C.
Okay, so let me keep marking here. We have one vote for A, one vote for C. Okay, we have few other people. I want everyone to answer something. Doesn't matter if it is right or wrong, right?
So option C.
Option C, 2 votes. Other people? You can just type. It's okay. You don't have to unmute. No? Okay. I guess some people are hesitant. That is fine. Okay. So we have two bodies, right? One is a black body and one is a white body or a white surface. And when we study black body radiation, the first thing that we study is we say that a black body is a perfect absorber, right? It is an ideal observer. So it absorbs every radiation. Whatever radiation you throw at it, it will not be reflected. Whereas white surfaces are exactly opposite. That is why people generally paint their houses white, right? It reflects most of the sunlight and your houses are cooler. Okay. So if you wear a black t-shirt on a hot day, you'll you'll feel the heat of the sun. But if you wear a white t-shirt, you will feel much relaxed, much cooler. Why? Because black body or black color in general that absorbs most radiation. That is why you do not see any color, right? Whereas, okay, what is white light? White light is just a combination of all the colors, correct? So if you are seeing a white object, what that means is it is reflecting every light, right? All the radiations that are going to it, they are getting reflected, and then you are looking at all the radiations, and then your brain is interpreting that light as white. For black body, it is not reflecting any light. Okay, no radiations at all are getting reflected. Therefore, what you see is black. And because no radiation is getting reflected, so then it means that they are getting absorbed. Okay, so therefore a black body absorbs more heat because heat is nothing but radiation, right? It will absorb more heat in compared to a white surface. Okay, any questions in this one? No? Good. Next one. So I'll write few names and you have to tell me which of these has maximum energy. Okay, again we will vote and you can unmute your mic or type in the chat box. Yes.
Sir, option A.
Okay, we have one vote for A. Pankaj says A. Other people?
Sir, X-rays.
X-rays. Okay. Okay. So I guess everyone is very familiar with this. So there is something called this spectra, right? The spectra of light, which goes like this. So I'm plotting this in terms of frequency, you know, which is also same as energy. Okay. So let's say your visible region lies somewhere here. Then your this will be your blue light, right? Blue has higher energy, and this will be your red light here. Red has lower energy, correct? And therefore, the wavelengths which are towards left of this red, they are called infrared, right? So this is your infrared region, IR, and those which are on the higher side of blue, they are, because this is okay. Let me not write blue. Let me write violet. Okay, and therefore on the right side they are called ultraviolet because they are higher than violet. So this is ultraviolet or UV, and then after UV you get X-rays here. Okay. Okay. So there is one more name which comes after X-rays, and it has even higher energies than X-rays. Does anyone know?
Yes.
Gamma rays.
Yes, gamma rays. Okay. So you are studying atomic and molecular physics, right? And in the lecture, it was told to you how X-rays are generated. So you get X-rays. So there are K alpha, K beta, all these radiations, right? And these you get because of atomic transitions. So your electron transitions from some energy levels to the other, and it emits a photon, and you get X-rays. Can you tell me how gamma rays are generated? Anyone? I mean, it is not taught in the class, but just for curiosity, because now you know how do you get X-rays. You know X-rays when there is atomic transition, so you have electron jumping from one level to other. It can generate X-rays. What will generate gamma rays? Mm, Does anyone know?
So I only remember something about decaying and releasing of energy.
Yes. So these gamma rays actually come from
So
nucleus.
when undergoes the radioactive decay maybe.
Yes. So that time you get all these gamma rays. So the origin, like for here in this case, the origin was your atom, right? These are atomic radiations. Your gamma rays, they are actually nuclear radiations. So as Pragya said correctly, you get these when you have decays, such as in nuclear bombs, and then in a nuclear bomb you get such kind of decays, and then you get nuclear radiations, which are very high energy radiations, and these are gamma rays. Okay, now why they are dangerous? Because as you can see that X-rays are high energy photons, and they are able to penetrate your skin, right? And then you can see the X-ray of your bones, right? Because these radiations, they pass through your skin and come back. Gamma rays can even penetrate your bones. Okay, so these are very high energy rays, and therefore they will enter your cells, and they will damage your DNA. Okay, and therefore these are very harmful radiations. Okay, so let's solve one more problem. I guess this we already discussed somewhat. Anyway, I'll just write according to Wien's displacement, which is correct. Okay. Option A. Okay. Answers?
So option B.
Option B. Okay. Any other answers? No. Okay. So this is this is just a displacement law, and this was determined experimentally. that, okay, I've already told you that this is the correct option. Can someone tell me what is lambda m and why does it have one m in it? Again, it comes from black body radiation, right?
Sir, as far as I know, it was the
Mm-hmm.
was emitting.
Sorry, I couldn't hear you. Can you repeat?
So the peak of lambda versus energy graph for the black body radiation, the peak where it was coming, that peak was lambda.
Yes. So when we plot, sorry, when we plot intensity versus lambda, right? The graph looks something like this. And this peak here, this is your lambda m. And this is for some temperature T. Now, if you change your T, the position of this peak, that will change. So if you increase your T, what will happen? Your temperature now increases, so your wavelength will
Decrease.
decrease. So this will shift somewhere here now. Okay, and it will keep on shifting like this. Right? Depending on how much you increase your temperature. So this line, okay, this is with increasing temperature. Okay. Now, what do you mean by decreasing wavelength? Decreasing wavelength means energy will increase or decrease.
So increase.
So energy will increase.
So
So what?
higher order spectra.
Yes, higher order spectra. So we just discussed spectra. What this means is that if you heat an object to very high temperatures, you will start getting all the higher order spectra. You will get UV radiations, you will get X-rays. I don't know if you can get gamma rays, but anyway. So suppose if at some temperature you are heating a metal and it is giving you red color, then if you increase the temperature, it will start going towards the blue side of the spectrum, right? And then it will even start radiating UV rays at even higher temperatures. Okay, so this is your Wien's displacement. Okay, now how can you use this thing? So let's solve one problem which tells you about the application of Wien's displacement law. Okay, so the problem is the sun, sorry, the sun gives maximum emission at 5500 angstroms. So this is the wavelength at which the intensity is maximum. So you get maximum emission at 5500 angstroms. And what you have to do now is estimate temperature of the sun, and it is given that the Wien's displacement constant, that is 3 into 10 to the 3 minus 3 meter Kelvin. Okay, and your options are 5500 Kelvin, 55 into 10 to the power 4 Kelvin, 5454.5 Kelvin, and 15,000 Kelvin.
Sir, option C.
Option C. Yes, correct. Okay. Uh, how do you do this? You simply write the Mises displacement law. So let me call the constant as b. Okay. So which means your temperature is b over lambda m. Okay. So your T is B is 3 times 10 to the minus 3, and your lambda M is 5500 into 10 to the power minus 10. Okay. And you can rewrite this as 3 over 55 into 10 to the power 5 Kelvin. And if you solve this, you will get 5454.5 Kelvin, which is option C. Clear? Any doubts? So what this problem tells us, that if you look at very distant objects like sun, for example, and if you record its spectra, okay, what radiation is coming at what wavelength, then by just knowing the where the maximum emission is, you can estimate temperature of these celestial objects, right? Okay, so basically you can make a thermometer using this rule.
Sir, does that mean that this law is actually like used for estimating temperature of all types of celestial body when it is observed through like any type of telescope?
So telescope will not necessarily give you the exact value of the maximum emission, right? Then you have, like for example, these Hubbard telescopes, the modern telescopes that you have. For example, people are also estimating temperatures of black holes, right? You guys must have seen photo of a black hole where they just modeled it using some image editing, but what they were actually capturing is the radiations, and those radiations are called Hawking radiations. And okay, this law, this is experimentally correct, and the value of the temperature that it gives you, I don't know how accurate this is, but it gives you a rough estimate, right? What is the roughly what is the temperature of a star, of sun or some other star? There are also many different kinds of stars, right? Dwarfs, giant stars, red giant, so on and so on. But using this very simple equation, you can calculate this thing. The problem which I think can come is in knowing the value of B. Okay, because this B it can depend on the material, right? It can change with one object to other. So how do you get the correct value of B? Okay, so then you have to take some rough value. Okay.
Okay, sir.
Okay. Okay, let's solve one more. So you have a spherical body. You are given the radius as 10 centimeters, and it is radiating 500 watt power at 500 Kelvin temperature. Okay. Now, if the radius is being halved, okay, and the temperature is doubled, and your temperature is doubled, the power radiated will be. So your options are these: 8000 watt, 4000 watt, 2000 watt, or 500 watt. Okay, so earlier you have one spherical body and the radius is 10 centimeters. This is kept at 500 Kelvin, right? Now what we have done is we have halved the radius, so it has now become smaller. Radius is now 5 centimeters, and temperature is now doubled, so temperature is now 1000 Kelvin. Okay, so earlier the power which was emitted was 500 watts, and now we want to know what will be the power now. Okay, so which equation will we use here?
So Stephen Boltzmann.
Yes, Stephen Boltzmann. Now, one thing to note in Stephen Boltzmann, okay, so we had solved one problem already. Let us go back here, right? We have solved this problem. Now, here I want you to pay attention to the units which we are using. What are the units? Energy per area per time, correct? This is calories per centimeter square per second. Okay, and this is proportional to your t to the power 4th. Okay, so let me come back here. Let's see. Okay, so we had u proportional to t to the power 4, and the dimensions of u are, so it is energy divided by area divided by time, and this is proportional to your t to the power 4. Okay, so let us take area to the other side. Okay, so your energy per time, then that is proportional to t to the power 4 times your area. Is this clear? Now we have temperature for both the cases, right? We have 500 Kelvin and 1000 Kelvin, and we have area for both the cases because we have the radius. Okay, or we can even simplify this area, and instead of area what we can do is we can write proportional to t to the power 4 multiplied by r squared, because area is 4 pi r squared, right? So we have now this thing. So your p will be, okay, so now we can write p upon 500. This will be temperature of p, which is 1000 to the 4th, multiplied by radius, which is 5 squared, divided by temperature of the white object, which is 500 to the power 4, and multiplied by 10 squared. Correct? Any doubts still here? So I have just made use of this proportionality, and I have written our equation like this. Okay, so you can just write this thing as 2 to the power 4 divided by 2 to the power 2, which is, so this is 16 over 4, which is 4. Mm, not D. So, okay. So we have, so this comes out to be 4, right? And so P over 500 is 4. So your P is 4 into 500, which is now 2000 watt. Okay, so C. Okay, Pankaj got D. Okay, I'll explain once again what we are doing. Okay, so the question says that we have a spherical body and they have given a radius 10 centimeter. Now, whenever you have a body, the radiation that it emits comes from its surface. Okay, so that is one thing that we need to know. So radiation comes from surface. Okay, so the larger the surface area, more will be the radiation. Correct. Therefore, you can see that your energy will be proportional to your area. Okay, and from Stefan Boltzmann law, we already know that this is also proportional to your fourth power of temperature. And area for a sphere is proportional to the square of its radius. So combining both of these things, we can write E proportional to R squared and T to the power 4. So if you half the radius and double the temperature, what will end up happening is the final energy, as we just saw, it becomes 4 times the initial one. Right? The power that you are getting, energy per unit time that you are getting here, that has now become 4 times. Correct? I hope this is clear now. Any questions in this one?
No, sir.
No? Okay. No, okay, good. So I am assuming that we have also studied Mosley's law in the class. This will be question 2, I guess. Right?
Yes, sir.
Okay. So let's solve one problem based on Mosley's law. So the problem is use Mosley's law with sigma is equals to 1 to find the frequency of K alpha X-ray for lanthanum. So lanthanum is La and its atomic number is 57. Okay. If the frequency of K alpha X-ray for copper, and here Z is 29, is 1.88 into 10 to the power 18 hertz. Okay, and your options are 2.88, Okay. Now, what is the expression for your Mosley's law? Anyone?
So frequency equals to C times bracket open atomic number minus sigma bracket close whole squared.
Or I can just write under root. Same thing, right?
Yes, sir.
Okay. So this is your Mosley's law formula. Now here sigma is already given to be 1. So let us rewrite this as C times Z minus 1.
So
Correct?
option number C.
Option number C. Yes. Correct. Okay. Now for the case of copper, you'll have copper. This will be C times. Here Z is 29, so it will be 29 minus 1 or 28C. For case of lanthanum, you'll have La, and this will be C times 57 minus 1, or this is 56C. Now what we can do is we can divide both these equations and we can write La upon copper, take the under root, and this will become 56C over 28C, which is nothing but 2, right? Now we can square both sides and write nu La is 4 times the frequency of copper. Okay, and the frequency of copper is given to us 1.88 10 to the 18. So if you multiply that, you will get frequency of La to be 7.52 10 to the power 18 hertz, which is option C. Okay, correct. So will this be higher energy or lower energy?
Sir, higher energy.
This will be higher energy, right? So what this means is that if you go towards heavier atoms, so because lanthanum is heavier than copper, if you go towards your heavier atoms, what happens to the energy of radiations which they are emitting? That increases, right? Notice that both are K alpha X-rays. Both are K alpha X-rays. Okay. 1 second, I'll plug in the charger. Okay. So as I was saying, as you go towards heavier atoms, the energy of the X-rays that you are getting from even the K alpha values, they are now higher energy X-rays. Okay. Okay. So let us solve one last problem for today, and this will be a problem from your textbook, Physics of Atoms and Molecules by Branston and Georgian. Okay. So this problem is problem 1.15 of Branston and Georgian. Okay. So the problem asks us that What is the difference in wavelengths delta lambda between the Balmer H alpha lines in atomic hydrogen and deuterium? Okay, let me give you some options: 0.9 angstroms, 1.8 angstroms, 3.7 angstrom, and D is 4.5 angstroms. Okay, now this will be a little lengthy problem, so please pay attention. First of all, let's talk about hydrogen and deuterium. So how will a hydrogen atom look like? So this is hydrogen. Okay, how will it look like? It will have a nucleus and an electron. Correct? Now, how many protons and neutrons are there in the nucleus of hydrogen?
So one proton.
Ah, and how many neutrons?
So zero.
Zero. Okay. So then its mass is, okay. Let's assume for this problem that mass of proton and mass of neutron both are equal, and let us denote this by m. Okay. So this is m, and this is your electron, and its mass is, let's say, small m. Okay, this is fine. Let's now draw deuterium. Okay, again it also has a nucleus and it also has one electron, mass is m. How many protons and neutrons are there in deuterium?
So one proton, one neutron.
Yes, one proton, one neutron, so its mass will be 2m. Correct? This is all good, right? Note that the charge is still, this is plus E charge minus E charge, and here also you have plus E charge and minus E charge. So the charge is balanced. Both atoms are neutral. Only the difference comes in when you consider the mass of your nucleus, right? So in case of deuterium, now your mass of your nucleus is 2 times. Okay. Now what we need to find out is the difference between the wavelengths delta lambda between the Balmer H alpha lines in atomic hydrogen and deuterium. So what is Balmer H alpha line? We already discussed it earlier. Okay. So you have levels like this. Okay. Let's say you have levels like this. So this is n is equals to 1, 2, 3. And for Balmer H alpha, the transition happens here. Correct? Right? This we uh, discussed earlier as well. Okay. Now, what is the, what is the Rydberg's formula? we can now calculate h alpha, sorry, the we can now calculate this h alpha wavelength for hydrogen and deuterium using Rydberg's formula, correct? Okay, so let us start with Rydberg's formula. Now we know that the Rydberg's formula works like this. Here you have R, and this goes as 1 over n1 squared minus 1 over n2 squared, correct? And what is the value of this R? Where R is m times e to the 4 divided by 2 h cut squared 4 pi epsilon naught squared times hc. Okay. Okay, now I want you to pay very close attention to what will happen if we just use this equation for both the cases. Okay? So this R which I have written, this is for your hydrogen atom, correct? When your Z is 1. Okay? In both cases, your Z is 1. Your atomic number is 1. Only your atomic mass is different. Okay. So till here, any doubts? If no, then we can proceed. Okay. Now what will happen? See, in both cases, this m is your mass of electron, E is your charge, which is same in both cases, and then your denominator is just some constants. You have h cut, epsilon naught, h cut, speed of light c, all these things. So your r is same in both the cases, right? So same in both the cases, same for, let me write H and D, hydrogen and deuterium, R is same. And we are considering Balmer series for both hydrogen and deuterium, okay? The transitions we are considering are same. So your N1 and N2 are same, N1 and N2 same for H and D. So the wavelengths that you will get, lambda H and lambda D, they will be same, right? Using this equation. So you will get the same values. Now there is a flaw somewhere here, and this flaw is also discussed in the lectures. We are doing, we are making one mistake here. Can anyone tell me what mistake are we making?
We are assuming that the value of mass will be same for H and D.
Yes, so what we are assuming here, as was also mentioned in the classes, we are assuming here that your that your nucleus has infinite mass, right? That the mass of your nucleus is infinite and your nucleus is fixed in one place and only your electron is revolving around your nucleus. However, that is not a very solid approximation. So therefore this R is also written as R infinity. Why? Because we assume that mass of your nucleus is infinite. But when we consider finite mass, then we write R as mu times e to the power 4 and same thing. Correct? Now here mu is reduced mass. Here mu is reduced mass. For hydrogen, let us write, for hydrogen mu h will be, so it is just m1 m1 m2 upon m1 plus m2. So if you have two bodies of masses m1 and m2, your reduced mass is simply m1 m2 divided by m1 plus m2. So what will be the reduced mass for hydrogen? We have mass of the nucleus, and then we have mass of electron, and then we can divide them like this. Okay, this is fine. Okay, now let us also, for just conventions, let us also make one definition. So we can write this as k times m. Okay, so basically what we are saying is that our mass of proton or neutron, in this case mass of our nucleus, that is k times m, and then this we know that the value of k is 1836, right? So our nucleus is 1836 times heavier than our electron, correct? So then here we can substitute k, and we can always talk in terms of mass of electrons. So your mass of proton is k times the mass of electron, right? So this becomes km squared and k plus 1 m. So this squared will cancel, and this become k upon k plus 1 times m. Correct? Okay. Now why we are doing this is, we are doing this so that we can write our Rydberg constant like this. So it will be k over k plus 1 times m e to the power 4 upon 2 h cut squared 4 pi epsilon naught squared hc. Now if you look at this term, okay, too dark. So what is this term? Okay. What is this term? This is simply r infinity, right? So then, so then you can write your r to be k over k plus 1 times r infinity. Is this clear?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. So when will r and r infinity become same? So if you take limit k tends to infinity of r, so this will be limit k tends to infinity k over k plus 1, right? If you take this limit times r infinity, now what will this limit come to be? Because now k is very large, so this will just become 1, right? K plus 1 will become k, and k will cancel out, right? So in this limit, this just becomes r infinity. And what does this limit mean? K infinity, what is k? K is the ratio of mass of nucleus to the mass of electron. If this if this ratio becomes infinite, which that means our nucleus has no infinite mass, right? Therefore in therefore we write a subscript infinity here. here, because this expression only holds true when we assume that our nucleus is very very heavy compared to electrons. Otherwise, this is a much more better approximation for the value of Rydberg's constant. Okay, fine up till here. Now what we want to find is the difference, right, in the wavelengths. So we have already calculated mu of h, right? Now let us calculate mu of d. So for deuterium, instead of m, we will have 2m, right? That is the mass of nucleus. Here you will have m, again 2m and m. Okay. Again, let us replace capital M by km. So this becomes 2k m squared upon 2k plus 1 times m. This cancels, and this becomes 2k over 2k plus 1 times m. Okay, this is fine. Okay, so now let us calculate the wavelengths. So let's start first with hydrogen. So we now have the wavelength for hydrogen, the k alpha wavelength. We can write it as this thing is equals to, okay, also let us call this as lambda naught, right? Let us call this as lambda naught. So lambda naught is the wavelength which we are getting when we are assuming that our nucleus is of infinite mass. Okay, let us just simply call this as lambda naught. Okay, so here we have 1 over lambda h and k over k plus 1, right? Here you have k over k plus 1 r infinity, and then simply this expression 1 over n1 squared minus 1 over n2 squared. Okay, now this thing is 1 over lambda naught, right, as we just wrote down previously. Okay, so our 1 over lambda h now becomes k over k plus 1 1 over lambda naught, and our lambda h then becomes lambda naught times k plus 1 over k equals to lambda naught 1 plus 1 over k. Okay, this is fine. Let us now do the same thing for deuterium. So what will happen for deuterium? So instead of this term, we'll now have 2k over 2k plus 1, because this is the effective mass now, right? This is the effective mass, and then this term will remain the same, which is basically your r infinity 1 over n1 squared minus 1 over n2 squared, and this is simply 1 over lambda naught. Okay, so then we can write lambda d to be lambda naught multiplied by 2k plus 1 over 2k which is equals to lambda naught 1 plus 1 over 2. Okay, clear up till here? Hmm? Clear?
Yes, sir.
Okay, so you can now see that our wavelength for hydrogen, it has now changed by this factor, right? And our wavelength for deuterium has also changed by some other factor. And because both of the factors, they are not same, right? The factors are different, correct? So the value of lambda h and lambda d, that will also be different. Okay, and that is what we have to find. If we go back to the question for a second, we have to find what is the difference in wavelengths delta lambda between the Balmer H alpha lines for hydrogen and deuterium. Hmm.
Is it option B?
Yes, it is option B. Okay, so we are almost there. Now, how do we proceed now? We basically want to find delta lambda, correct? So delta lambda is nothing but lambda h minus lambda d, and you can write this in terms of lambda naught, and this will be 1 plus 1 over k minus 1 minus 1 over 2k, correct? Let me know. Okay, and if you simplify, you will get, so this 1 and 1 will cancel, and then you will get 1 over k minus 1 over 2k, and this is simply lambda naught over 2k. Okay, so your delta lambda is lambda naught over 2k. Okay, and now what was our lambda naught? Our lambda naught was given by this expression.
56.5 nanometer.
Yes, so we can simply, if you remember, then it is very good. So it is 656.5 nanometers. If you remember this number, then it is very good. This is actually the H alpha wavelength number. Okay, and this comes in when you plug in the value of R infinity and the value of N1 and N2 as 2 and 3. Okay, so your lambda naught is basically 656.5 nanometers. Lambda naught 656.5 nanometers. Okay, and what is the value of K? So K is the ratio of mass of proton to mass of electron. What is the value?
So 1836.
This is 1836. Okay, now we have all the values. Let us plug them in. So our delta lambda is then 656.5 divided by 2 times 1836 nanometers. So if you solve this, you will get 0.18 nanometers roughly. Okay, and then if you convert it to angstroms, this will become 1.8 angstrom. Which is your option B? Okay. Any doubts in this problem? Anyone? This was a little lengthy problem. So if you had doubts anywhere, or if you felt some portion was little hazy, I didn't explain properly, We can discuss that again. Okay. If not, so let me then explain what is the crux of the problem. So why are we solving this problem anyway? Okay, so as we discussed in the beginning, if we do not consider the effect of mass of nucleus, right? If we assume that the mass of nucleus is very, very heavy and we need not consider it in our calculations, then we cannot explain why we are seeing the wavelengths in the atomic spectra of hydrogen and deuterium at different places, right? So in class, what sir discussed was you have like radiations like this. So this is H alpha, H beta, so on. And then very close by, you also observe other radiations, right? And this was not discovered in the beginning. These radiations, okay, let me write H alpha, H beta, so on. Okay, your wavelength is going like this. Sorry, your wavelength is going like this. Okay, so this was not observed in the very beginning. For example, this Balmer series, uh, which was discovered by Balmer, I think this was done in 1836 or somewhere around in 1800s. Basically, I don't remember the exact year. But you can see in at that time you will not have very high quality spectrometers, right? And sir talk about resolution in his lecture, right? Resolution of your spectrometer. Okay, so you need high resolution spectrometers to separate these two lines. If you have a low resolution spectrometer, these lines will just appear one and they'll appear much thicker. So you'll observe some line like this. Okay, now you cannot tell if this is a combination of two lines or this is just one line. You don't know, right? Because now it has some thickness and this is coming because of your instrument, right? And then this distance d, this is what you call as resolution of your spectrometer. So as time progressed, people were able to make better quality spectrometers. After that, they started observing these lines. Now why do these lines come? Then there was a discussion, and then finally when you it was resolved when you considered that there is a isotope of hydrogen called deuterium, and these wavelengths are coming because of deuterium. So you can just take hydrogen or you can take deuterium, and then you'll get these values. If you have a mixture of hydrogen and deuterium, you will get both the basically both the spectra collectively. Now the purpose of solving this problem is to get this value 1.8 angstroms. You can see that this value is very small, right? This is 10 to the power minus 10 meters. So you need very, very fine spectrometers to get this value. But once you have the spectrometers and your resolution is less than 1 angstroms, okay, if your resolution is less than 1 angstrom, then you can separate these two, right? Because this distance is roughly 2 angstroms, right? So then you can basically separate, you can see both the radiations. Now why this is important? Like for the case of the problem we solved for Wien's displacement law, we said that we can somehow estimate the temperature of celestial bodies. What can we do with this uh, spectral analysis that we have just discussed? Any idea? So I just gave a hint that it is related to isotopes, right?
So then we can differ the elements which are radiating the wavelength.
Yeah. So We can differ the elements, that is correct. But for that, we do not need, we do not need to consider this effective mass thing and all, right? Because for different elements, the wavelength shift is of that or in the orders of hundreds of nanometers, right? Or maybe not hundreds, but tens of nanometer shift is there. This is just a zero point 0.1 angstrom shift, right? The order is different. With this small shift, what you can do is you can get the isotopes. Like, for example, you must have heard of a term called carbon 14 dating. Yes? No?
Yes, sir.
Okay. Now, what is carbon 14 dating? Any idea? So it is called C14 dating.
Sir, it is used to approximate the uh, like the age of the particular item, how old it is.
Correct. Now, why that happens is, okay, so you can have a sample and it can have, so this is like, for example, you can have some fossils, right? And because it is a fossil, it will have some organic molecules. And because it will have some organic molecules, there will be some carbon. And there will be some carbon 14 and there will be some carbon 12, right? Some different percent. Let's say this is X% of the total carbon that is there. Because now, I don't know if you guys have studied these nuclear reactions where you have the mean lifetime and half lifetime, all these things of nucleus. What basically happens is your carbon 14 nucleus, it decays to a carbon 12 nucleus. Okay. And by knowing that how much carbon 14 has decayed, you can get an estimate of how old your fossil is. Okay, you get the idea about the age of the fossil if you know the percentage of the two, carbon 14 and carbon 12. Okay, now how do you get this experimentally? Just like we discussed right now, you can measure the intensities of these two different lines, right? So if you have a very good spectrometer, it will resolve the carbon 14 and carbon 12, right? And one, let's say, has intensity I1 and this has intensity, let's say, I2. Okay, this is, let's say, carbon 12, this is carbon 14. Just like how we calculated for hydrogen and deuterium, you can use the same approach, right? You can use exactly the same approach. And here in R infinity, you will also have to consider the mass of your nucleus, and then you will have a factor of z coming in here, right? A factor of z will come in. Okay, anyway, then you will be able to get this separation d, right? And then you know which one is carbon 14, which one is carbon 12. So carbon 14 will be, if this is your wavelength lambda, your carbon 14 will be towards left, right? Because carbon 14 is heavier than carbon 12. And then you can get the intensities I1 and I2. And then using the intensity ratio, you can estimate, okay, what is the age of the fossil. Okay. So that's why we study all these things, because they have potential applications. They are not just some textbook things. Okay. And if you are interested, I would recommend that you go and study a little bit about carbon 14 dating and what is the half life cycles and how you can, if you do some nuclear physics course, you will for sure solve some problems related to carbon 14 dating. So you can even refer some physics textbook where they discuss the decaying of nucleus. Okay. Um, and if you have any doubts, you can ask me in the forums or the YouTube comments. This video will be uploaded to the YouTubes. I hope you guys get the links on NPTEL websites, even for the last tutorial which we had last Saturday. Okay? If not,
Yes, sir.
yeah, okay, great. So you guys are getting the links. Uh, I'm glad to hear that. So yeah, feel free to ask questions in the forum. I'll reply if you have any doubts. And okay, let me again put my email ID here. I'm available almost every day, and whenever I have time, I will reply to your emails. Okay, so this is Manav Beniwal at isc.ac.in. Feel free to email any doubts, or not just doubts, if you want to discuss anything physics related or even career related, what you want to do. Feel free to send me a mail. We can set up a meeting, we can discuss. Okay, with that, I'll wait for like 5 minutes to see if anyone has any doubts. We can discuss. Otherwise, you guys can leave the meeting. So I'll be here for some 5 extra minutes. Yeah.
Thank you, sir.
Yeah, you're welcome. I'll see you next Saturday.
Thank you for the session, sir.
Yeah, you're welcome. Thank you for the interactions. Uh, your interactions really made the session better. Okay, thank you. Yeah, you're welcome, Pankaj. See you next Saturday. Bye bye.
Can I leave, sir?
Yeah, if you do not have anything to ask, feel free to leave.
Okay,
If
thank you,
anyone
sir.
wants to ask anything, they can stay back. Okay, you're welcome. Bye bye. Have a nice day.